Good afternoon. Welcome to a Building Knowledge Enbridge, and in this case, Building Enclosure Labs webinar presented to you on big buildings, small holes, measuring, reducing air leakage and large multi-residential and commercial buildings. My name is Gord Cooke. I'm pleased to be the host and facilitator. Really excited about this topic. We're very pleased that Enbridge, one, has been running a program for a couple of years, and two has agreed that this would be a good opportunity to kind of touch point and see where we're at, see how things are going, and announce a continuation of the program that they've been working with. We'll give people just a minute or so to sign in, but we have a nice intimate crowd, I would say. Your will be put on mute. You'll be left on mute and camera off. We will have a chance for questions at the end. If you do have questions throughout the session, please put it in the Q&A. For those of you familiar with Zoom, put it in the Q&A. If you just want to make a general comment, put it in chats. But if you actually want a question answered, it's way easier for us to track. And down the road, it's easier for us to answer. If we don't get to answers, we will put them. It's better if they're in the Q&A. We have online with us Emma and Kimberly from our Office of Building Knowledge. If you're having any technical issues, put that in the chat, and they will from time to time put some resources, links and so on in the chat as well. So make sure you're checking on that. The timing on this is 1 till 2:30, so an hour and a half. As I say, we'll have time for questions. I think given the format, we'll ask you to hold your questions, that is, put them in the Q&A. We won't necessarily answer them right away. So we're at 1:02, and so I think if everybody's okay with that, we'll get started. I'll introduce you initially to Venoth Jeganmohan from Enbridge. Good afternoon, Venoth, and I'm sure you'll want to welcome everybody and just kind of give a little bit of background of what your role is at Enbridge and how this market transformation program is working.
Thank you, Gord. I want to thank everyone today for joining us on this webinar. My name is Venoth Jeganmohan, as Gord mentioned. I am the Energy Solutions Advisor at Enbridge, who manages our commercial air tightness testing incentive. This program is one of many that support our commercial new construction markets to lower energy efficiency and promote higher efficiencies across the board. As part of this webinar, we're here to explain how the commercial air tightness testing incentive currently works, some of the benefits on why you may want to choose to perform air tightness testing for your buildings and future projects, and the process that's involved. You got a next slide. Before I get started, I just wanted to really go quickly through a land acknowledgement. Today, we acknowledge that the offices of Enbridge and Wellbeing Partnership stand on the traditional territory of many First Nations people. We honor the Mississaugas of the Credit and the Anawabu and the Chippewa and the Handusani and the Wendat peoples, the original keepers of the land. We also acknowledge that Toronto is covered by the Treaty 13 with the Mississaugas of the Credit. Can you go next slide, please? A little quick history about Enbridge. You guys obviously know us as the gas company, but we also offer a wide range of energy conservation programs across all industries, whether it be residential, commercial, or industrial. These programs are aimed at lowering total emissions and improving the efficiencies of the overall network. Today, we're here to talk about one specific program, our commercial air tightness testing incentive. Can we go next slide, please? Before I go there, I want to talk about some important numbers that may be relevant to you if you're in the builder space, especially. First, we have our builder and attachment center. This is for any new gas connections and meters and project numbers. It's a 1866 number, as well as our customer care. This is more for forms, billing issues, meters, safety installations, all of that type of jazz. So these two important numbers will be mentioned in the chat, and you can jot these down in the future if you need them. Next slide, please. So the way our commercial air tightness test incentive works is we currently are incentivizing 80% of the cost to do a commercial air tightness test. Um, there is a maximum cap for this test of $30,000 per project. And for those who participate in the air tightness testing incentive, we also have a second portion. We call it our implementation incentive. This is provided for areas of envelope improvements that are done to a project. Some examples that are mentioned here are aero barrier, caulking, sealing, but it can really be any type of envelope improvement that you're looking to do that can reduce your overall envelope leakage. We can incentivize up to 50% or a maximum of $15,000 per project for the actual implementation measure. Some examples of things that I've gone through in the past have been spray foam. There's particular areas of the walls or cavities that want to get spray foamed, we could help incentivize that to improve the leakage. And this incentive is really in the marketplace as we're trying to develop the commercial testing throughout Ontario. Currently, as some of you may know, like the residential market, this is very common and a mandatory requirement for the Ontario Building Code. In the future, with the adoption of Toronto Green Standard, this may become a mandatory practice. And so this incentive is giving builders and developers a chance to perform air tightness testing before it becomes mandatory practice. There's a lot of great benefits with performing air tightness testing that you're going to learn about shortly. And this incentive is really meant to promote the industry and to get more buildings tested. Next slide, please. Now, to be eligible, so as I mentioned, this is for commercial buildings. So anything under Part 3 scope of Ontario Building Code would be eligible. And there is a minimum size requirement of 25,000 square feet or larger. You need to be located in an Enbridge service territory, which is most of Southern Ontario. That little orange map here kind of highlights it. But if you reach out to me, I can let you know if you have a project that's maybe not that might not have natural gas available. And we are currently incentivizing either testing of a whole building using a whole building approach or guarded. Individual zone testing or floor by floor testing only is not eligible as part of this program. Next slide, please. So if you want to get started and learn more about this incentive, you can reach out to me. My email is shown here and I'll put it in the chat. We can set up a call and we can walk through your project to see if this incentive will work for you. And if you had any questions about the process or applying. Next slide.
And thank you, Venoth. The program's been running about 2 years, as I recall. You've seen some pretty interesting projects come across your desk, I'm sure.
Yes, it's actually been really successful program. It's been this is actually the 3rd year of operation that has been in the market, but it's still not as well known as we like. So that's why we do things like this, these webinars to gain market awareness and to spread the knowledge.
And it truly is market transformation. You're going to hear us talk about creating a database of results because there just haven't been that many large buildings done. So this afternoon, then between now and 2:30, we'll do. You'll see a bit of introductions. We're going to do a very quick review. This is meant for, I'm going to say, a knowledgeable audience. If you find these first slides are confusing or controversial in any way, please reach out to us because we'd be happy to put a different seminar on that talks about why build airtight. But in general, we're going to move through that pretty quickly. We'll talk a little bit about airtightness and codes and standards, but it's really about experiences. First, Kyle from Building Knowledge will give you some of his experiences, 4 to 5 different projects. And then we're really excited to have Randy Van Straaten from Building Enclosures Labs to talk specifically about guarded testing. Randy, it's kind of an interesting one, so I'll leave it for the moment, but I'm really excited to hear what you have to say. And then we'll come back and look yet again at the testing program just to make sure we have the specifics of that. Go ahead, Kyle, next slide. So there's my name and address. I bought my first blower door back in 1987 doing new construction, R2000 work. About 7 to 10 years ago, we outfitted our company. We have up to 18 blower doors that we can mobilize on any given day. So we would like to be your testing partner in the industry. Those who are interested in, we're one of several firms that will do it. We would encourage you to contact any of us, but that's kind of our background and experience. Next, if you wouldn't mind. There's Randy, as you can see. Randy's had a long time experience with in the fields of building science and specifically on air tightness testing. Randy, say good afternoon.
Yeah, good afternoon, everyone. I'll share a few more slides at the start of my presentation as well, so you'll get a sense of who I am.
You were just telling me down there at the bottom there that you did some work in outer Mongolia and you feel like there's a blower door acting as a coffee table still somewhere there.
Hopefully they're using it. I hope it's not collecting dust somewhere. Yep.
Fair enough. Thank you. And then next slide. And you're seeing Kyle on the screen as well. Kyle is one of our senior project managers with Building Knowledge Canada, over 15 years experience. And Kyle, you're going to report today on some interesting case studies that you've worked on. Just go ahead and introduce yourself.
Absolutely. Yep. Nice to chat with everybody today. And yeah, we've been working on building energy efficiency for a while now. Various programs like Energy Star, LEAD, EnerGuide, and lately my focus has been specifically on managing these large building air tightness testing projects. Me along with Michael Gillizan, who's also listening in on this.
Yeah, Mike's here, and if we have any specific technical questions, Michael, so that's great. You have a nice team there, and again, mobilize weekends, evenings. That's kind of you to be able to do that work on off hours. So thanks for that, Kyle.
We got to be pretty flexible in this line of work. Yep.
Exactly. Thank you. Next slide, please. Okay, so let's start that conversation. Here's a really nice one of the leaders in the industry of RDH out in BC, Lauren Rickards, who did a pretty interesting study on air leakage in buildings. And notice on the right-hand side there, you're seeing the various control functions in a building, and just want to talk about air tightness as part of that. And notice the 4 underlined terms on the left-hand side: the durability, comfort, air quality, and energy consumption. That it's important in all buildings for those 4 reasons to do air tightness. And again, if you find that doesn't match with your current thinking, please put it in the chat. We'd be happy to book a session, whether it's an Enbridge session or whether we just come to your office. We'd love to talk to you about that. Understand that air tightness testing of large buildings is becoming more and more mainstream. Army Corps of Engineers in the United States for at least 10 years now has required every one of their buildings frankly around the world to be air tightness tested during construction. So just a little example of how things are moving. We'll go to the next slide. I mentioned durability, and in fact, air tightness requirements made their way into the building code specifically for this reason. It wasn't for energy efficiency. It was to ensure that warm, moist air didn't get into colder cavities that are getting colder and colder because we're insulating more and more. That is, the more insulation you add to a cavity, whether that's a wall, a ceiling, a floor assembly of the top of a garage, for example, the more insulation, the more chance there is for interstitial condensation. That's why air tightness made its way into the code. You can go into the next slide. So first and foremost, it's the durability, and just showing examples of that. Efflorescence, well, is that doing damage to the building? Well, certainly doing damage to the aesthetics of the building. And at this point, it's showing that the moisture is being driven to the outside. And you might say, well, at least that's a good thing. But what if it's being driven to the inside? And what kind of damage might it be doing? So we see examples of this, the geeks that we are, walking or moving around cities in North America and seeing these kinds of damage, going, gee, I wonder if that's air leakage. Next slide, please. This is more residential lurking. This is a townhouse complex, but the understanding of ice dams, that is warm, moist air getting into attic assemblies. In this case, the moisture is being presents itself on the outside because of that warm, moist air leakage, raising the temperature of the roof deck and therefore causing ice damming. So pretty dramatic cases that you're seeing here, but this too was related to air leakage. Next slide. Of course, the new metric, if you will, the new interest is in heat loss, and all of the studies have shown that specifically in tall buildings, most buildings, frankly, air leakage represents 20 to 25% of energy loss. And you might say, is that proven? And the answer is yes. There's been numerous studies done on this over the years. And understanding that tall building, we know one thing for sure: warm air rises. And the taller the building, the greater the stack pressures and the more acute the energy losses can be. You can also start to imagine the comfort effects of this kind of air movement. But certainly from an energy perspective of how much energy we're using or how much energy you need to replace in the building, sizing of equipment, this can be pretty vital. Next slide. Imagine this: warm air is leaking out of the top of the building, which means cold air is leaking in at the bottom of the building. And if the building happens to be connected to radon-rich soils and the sewer and other soil gases, then that too creates a problem. So air tightness now becomes I'll say health and safety requirement to make sure that we don't have uncontrolled leakage of radon and other soil gases into houses. Next slide. And I promised you I was going to do these quickly, but then I'll add to it the anomalies that we get. Imagine this: we used to play hockey in the wintertime, and now we're playing hockey in the summertime. So now we're thinking about moisture that's coming from outside, not from inside the building, but moisture coming from the outside and now impacting the interior. So in the winter, we're worried about warm, moist air escaping. In the summertime, we're worried about warm, moist air coming into the building. This has huge impacts on your dehumidification loads in all buildings. And obviously a pretty interesting example. Look at the bottom right. I've seen this I was a hockey referee for 44 years and refereed in the summer and had to find myself stepping around the telltale signs of air leakage into building assemblies in rinks. Next slide, please. And so there are these three drivers of air leakage, and I think all of you will understand. On the left-hand side, warm, moist air rising. Wind effects are pretty interesting, especially in tall buildings, in downtown urban areas and the impacts of that. And then, of course, mechanical systems. And the interaction of all three of those means that we could have air leakage. And the air leakage is difficult in any particular building on any given day to figure out where it is. We learned a long time ago that it was easier to control the holes than it is to control the pressures. That is, the pressures are always going to be there, and they're going to vary dramatically from day to day. What is very definitive and very definable is the air leakage points. And when I control the air leakage, I can negate much of the pressure impact, the impacts of the pressures that are common to all buildings. So that, in a very clear nutshell, is why we need to control air leakage. We'll go to the next slide. It is indeed listed in the Ontario Building Code, the National Building Code. It's been codified since at least 1995. These phrases, since 1995, 20 years. Is that 30 years, I guess, 30 years. It's been in the code. And look again for the highlights. To maintain comfort for intended use, to minimize accumulation of condensation and precipitation, to control heat transfer and ice damming, and to control radon and other soil gases. The very things that we know to be true, the building code has said so for about 30 years that this should be this is something that should be controlled. The measurement of that is a little bit different. And down at the bottom, you'll see that they've also tied it into SB 10 and the National Energy Conservation Standard for energy efficiency is also included now as part of reasons for air tightness testing. Go ahead, next slide. The metrics, the common metric for those who are newbies, I'm hoping all of you are experienced, but perhaps not, is to think about the amount of leakage as a function of the surface area of the building. That is the exposed or exterior surface area of the building. So we're talking floors, walls, ceilings, if you will. Anything that's separates conditioned space from unconditioned space, measured here in meters squared. And we look at the amount of air leakage at a pressure of 75 pascals. And you might well ask, why 75 pascals of pressure? For those who need a conversion, that's 0.3 inches of water column if you're an HVAC person. Why 75? Well, actually, Randy may have a comment on that. Randy, do you happen to know? I happen to when hearing Harold Orr talk about it, he chose 50 because it didn't implode the building, it didn't suck cats out of the building. It seemed like a good number that allowed us to feel the air leakage. And I believe commercial chose 75 just because residential was at 50 and 75 seemed like a better number. I may be shortchanging that. I think, Randy, you're probably going to tell me that it's the way we test materials as well. The pressure used across, say, a sheet of drywall or a sheet of WRB that would say how much air leakage is. Any perspective on that, Randy? Is why 75?
Yeah, I think material testing has drawn that 75 Pascal number from commercial whole building air tightness testing. I've always explained to people that my understanding is it's higher because as you have buildings that maybe sit above the tree line, you have more wind effects. And so if your standard pressure is at a higher pressure, if you have sort of plus or minus 10 Pascal wind effect, you can drown that out a little bit with this rating.
Yeah, fair enough.
But I'm not sure if that's true either. I wasn't around when they came up with it.
Yeah, either was I. Well, I was sort of peripheral, I'll say that to it. I'm down here in Minnesota, the Energy Conservatory, Gary Nelson, would probably give me a definitive answer on that, the makers of the Minneapolis blower door. You're seeing here on the page some of the leakage standards. I mentioned Army Corps of Engineers, Toronto Green Standard have normalized these, or at least provided test marks for these. Sometimes they're guidelines, sometimes they're requirements. There is only in Vancouver, Canada, sorry, in BC, is the requirements in code for testing large buildings. But if you're working with voluntary programs, voluntary incentive programs, you are going to want to work to that. And I just want to remind you, it's liters per second per meter squared at 75 pascals, normalized based on the envelope surface area of the building. We'll go to the next slide. Fair enough.
Just a note about the SB10 and
Thank you.
it references these codes, but older versions, I guess.
Yes, exactly. Thank you. So next slide. And we will highlight the difference between testing materials versus assemblies versus the entire building enclosure. So bottom in the middle there, it talks about they test materials, and to qualify as an air barrier, it has to have an air leakage of no more than 0.02 liters per second. That is, if you wanted to say that your water resistant barrier was also your air barrier, or drywall was your air barrier, then you would say, is it tested at 75 pascals? What's its leakage rate? That actually was determined. Basically, drywall was considered the first of the air barriers. That's about its number. So they said, okay, anything better than that shall be qualified as an air barrier. The second test standard is on assemblies, where we take say a wall section with a window and a door in it. This is, I think it's 2357 is the ASTM standard for testing. And here, it's roughly 10 times, knowing that there are going to be joins and leaks in that building, a little different. And then 10 times higher than that, a rough standard, and Kyle, you've put it in red. It's not a code requirement, but it's an often used guideline to indicate a whole building air tightness. Is that a nice way to characterize it?
Yep, exactly. Yeah, it's I like to just kind of make sure that point gets addressed, because sometimes people get confused about the different test metrics they see, and they get confused thinking the whole building test needs to be 0.02 or something like that.
Right.
But it's easier to think about the order of magnitude difference between
Right, 10
materials.
times order of magnitude. You're right, and thank you for that, because we have responded to specs where somebody uninitiated would say, if the material is 0.02, certainly you guys could make the whole building 0.02, and actually that's not the case. So thank you for that, highlighting that. And next slide, Kyle.
Oh, sick. There we go.
There we go. And so I'll highlight and say we geared up in about 2017, 2018. As I mentioned, we now have up to 18 blower doors that we can mobilize, and we just saw ourselves. We were doing it residentially. We knew the industry was going to move towards large building, and we wanted to help build that industry. So there's, as I mentioned, other really good firms doing this kind of work. But we've been really excited to do testing throughout Ontario. And Kyle, you're saying 70, and I think today you're going to show us 4 or 5. But just to highlight, multi-residential, churches, sportsplexes, I did all the sports rinks, all the rinks that I refereed in for 40 years, you guys tested, which was kind of cool. fire stations, which has its own security issues, some really cool stuff. And as you've indicated, builders, engineering firms, building owners, architects, and seeing, and you're going to speak to this, but that range, maybe I'll push it over to you and you take it from here for the next 20 minutes or so, and walk us through some of the results.
Sure. Thanks for that, Gord, and thanks for your concise summary of sort of the why we're doing this. So yeah, just to discuss a bit about the history, I've been testing large buildings just in the last few years. Michael and I have taken on the mantle from Rob Johnston, who really got things kickstarted back, I'd say just under 10 years ago, maybe, starting some of these large buildings with Gord. And so he's since retired. And then between Michael and I, we've been handling a steady increase in requests for this sort of service. So the drivers we've seen, it hasn't been one or two things. It's been quite a range. So there's been the municipal green standards that have started ratcheting up. Toronto green standards, a big one, just because we're in the greater Toronto area. A lot of projects now have test specifications for quality assurance purposes, and I'll discuss a little bit more about that later on. There's incentives too, of course, like the Enbridge one we're highlighting today that provide builders a little bit of a boost to get this done. Requirements for performance certifications like FIAS, net zero, zero carbon building is one that pops up. I think that's through the CHBC. And then a lot of municipalities are involved with these energy retrofit feasibility studies too. So we've been getting a lot of work from that. So some of the test specifications we receive, well, sometimes projects don't really have much at all. They sort of approach us asking what we would suggest to them, and that's okay too. Many, like I said previously, are mentioning the Toronto Green Standard testing or the zero carbon, etc. And then within a project spec, sometimes there'll be detailed description of what's required in Division 0140 under quality requirements or 0135 special procedures. So we're seeing sometimes some very detailed requirements, whether it's air barrier training to do, multiple test iterations like a mock-up or a mid-construction. They'll throw in detection of air leakage locations. They'll choose different test standards or protocols, performance targets, etc. Just to give you an example, here's the description of the TGS standard that we see a lot, and it's under their building energy and emissions and reliance category. And they've got a target of less than 2 liters per second per meter squared. And they do try and emphasize that it should be part of the building enclosure commissioning agent's scope to have this air tightness testing built in among the other things that a building enclosure commissioning agent should be looking at. So as I was mentioning earlier, there's can be quite a range. So sometimes it's just a basic final whole building air leakage test. And then other projects are interested in really dialing in some of the locations of the air leakage. Other projects want to do mid-construction air tightness testing, which can work depending on, you just have to be really clear about establishing what your test zone is. And if there's incomplete openings, how those are going to be sealed. And so sometimes mid-construction testing is valuable for quantitative testing, like predicting what the NLR could be. Other times it's maybe more useful for just, I like to consider a qualitative test, just to identify that certain assemblies are are in fact airtight and there's no leakage coming from areas where there shouldn't be. So both are useful. But you just have to be careful when you're specifying mid-construction testing and you've got a building with a lot of large openings that aren't finished. It may not be reflective of the end result. So it sort of varies from project to project, the usefulness of it and the practicality. So I'll go over some case studies. So this one was the Western University's Ronald Schmeichel. I believe that's not sure the pronunciation of that. But anyways, it was Western's first net zero energy building. And we used 2 triple kits, I believe, for this one. It's a 100,000 square foot building built in 2024. We tested it right at the pre-occupancy post-construction, mostly complete except for a construction hoist opening that needed some intensive sealing there, but we scheduled it for the evening time, so not many people in the building, which is perfect. The building didn't have little to any operable windows, and we did both a positive and a negative test. Not a whole lot of difference between the two, but the end result was a really impressive 0.57. So that's one of the better tests we've had. Go ahead, Gord.
And Kyle, you mentioned triple doors, and folks perhaps would need to know that each fan moves about 5,000 CFM, depending on the manufacturer of the fan. In this case, you only have a certain number of man doors, so you can put 3 fans, as many as 3 fans into one door. So you imagine 6 doors times 5,000, so roughly 30,000 cubic foot per minute capacity. And then you would decide based on your initial analysis of, gee, how many do I think I'm going to need? That is, I know the volume of the building. You would do before you get there a little calculation to say if the target's 2 liters per second per meters cubed, okay, let's do the surface area calculation. How many doors do you think we would need to get there? Have I got that?
Exactly. Yes. Upfront planning, figuring out a rough idea of what the building dimensions are, and that helps you gauge, okay, how much equipment am I going to need? And it also depends on the layout of the building. Like if you've got a building that's got a lot of spaces that aren't totally interconnected, you might need some more hits just to distribute the pressure properly. But if you've got a decent amount of interconnection with interior doors, then that makes the process simpler.
And you were pleased to tell them that they had a good result. So that's a good one. Let's go to another one and see if we're able to maintain that those levels.
Yeah, so this was part of a multi-building project with the city of Cambridge, and it was a net zero studies project. So the city hall, and I know Randy, you had mentioned this one was this one that you had worked on back in the day?
Yeah, I helped with the original design of the building back when I
Cool.
was a 20-something-year-old lead consultant ages ago.
Very
Intermodal
cool.
engineering. Yep.
So it was from 2008, if I have it correct, when it was finally built and commissioned. So 85,000 square feet, LEED Gold certified. I don't believe it was originally air tightness tested. I don't think that's a mandatory. So LEED requires testing of dwelling units, but not necessarily whole buildings. So yeah, we scheduled it for the evening. Once all the city workers had left, there was still some custodial staff present, no big deal. And it was a bit, the shape of it was a bit spread out. So we actually had 3 triple fan blower doors, so 9 fans total. And it ended up with a pretty respectable 1.1.
I was going to say, Randy, you proud of that number? That's got to be kind of cool to see.
Yeah, I'm guessing that's pretty average for buildings of that age.
Fair enough.
It's
Yeah. And that type.
Not all offices have the operable windows. This one did. So that could be one of the factors. But yeah, I think as far as existing older buildings, it did pretty well for that kind of building. And I mean the layout of it was it wasn't necessarily just a single box, right? It was kind of spread out a little bit. Had some interesting shapes to it. So another one, the Dell Park Home Center in Oshawa. This was one of the bigger ones we've done. And it was with the
20,000 square feet. That's pretty
it was 220,000. So it's got 4 ice pads, swimming pool, gymnasium, fitness center. So, and we had to do it late at night. That was not easy because we didn't want to have, like, these facilities run pretty late in the day, right? So we had to wait for the custodial team to be done so that we could start running our wires everywhere. So it required some careful planning, especially on the rooftop where you're up at night sealing off different mechanical vents. But it also achieved a pretty good number. And I'll go a little bit about some of the trends and results we're seeing later on, but 0.92 liters per second.
And pretty important, right? In a building like that, imagine the risk factors, that warm, moist air of the swimming pool, the coldness of the ice rinks. If we know that air tightness was first and foremost a durability issue, this is highlighting the need for tighter and tighter in buildings at higher risk. The higher the risk, the tighter you need to be from a moisture perspective. So that must have been a cool project. Kyle, that's great.
We tested some other ice rinks that weren't quite, now this was an ice rink plus, right? But yeah, some of the other ice rinks were a little higher, and you always have to be careful about, okay, where are the leaks?
Right.
It's good if the overall result is good, but yeah, if you've got some leakage in certain key areas, you might still end up with those problems.
Yep.
Then a couple more case studies. We've been working with Mattamy on a lot of their new Part 3 multi-res projects as part of a benchmarking study. They're really trying to get a sense of where their buildings are at to prepare for the Toronto Green Standard testing requirements. So one of them was in Oakville, the Clockwork Building 1 there, with a respectable 1.24, which I'd say for that type of building, that style of building, it's not too bad because there's a lot of operable openings. You got to think it's a pretty high building. The other one was TTC Russell Car House in Toronto, part of a net zero energy study. And I don't think going into this, we knew it would be pretty leaky. And sure enough, the result was 3. And they had and 15 overhead doors, and you could see daylight sort of everywhere leaking at them. So we figured.
And I am interested, the Mattamy was one that was done under the Enbridge funding, so that was kind of cool. Venoth, these are the kinds of buildings that you imagine, right, that are perfect for this program to kind of get that benchmark, to give people an understanding of where buildings are at and how we can improve. So kind of cool to see this this project come to fruition. Nice.
So I've gone over a few of the case studies, and just to kind of give an overview real quickly on what project teams can expect, because often it's just a big mystery of, well, what does this testing involve? How much is this going to inconvenience me? So the day of the test, it's typically 4 to 8 hours where we're on site. Most of that time is preparation for the test. So setting up the equipment, getting the building ready, usually propping open interior doors, making sure all the windows and exterior doors are closed, coordinating HVAC. So we need to make sure no outdoor air is being brought into the building or indoor air being exhausted out while we're testing. So we need to power down those systems. Depending on the test protocol, there's some protocols where it's more of an as operated state, and others are like a building envelope state where you want to close up certain mechanical penetrations. And that just requires us to do some extra sealing of vents. So once the building's prepped, we'll do an initial pressurization, make sure we're just confirming what kind of induced pressure we're getting, making sure we didn't miss any large openings or prep items like good example is, oops, somebody forgot to close the roof hatch. So you want to just make sure you don't leave anything obvious like that open at the start. Then when it comes time to do the test sequence, it's usually not too long. It's probably shorter than most people assume it's going to be, maybe 30 to 60 minutes, depending on the wind conditions and if we're getting the odd occupant coming and going out of the building, we kind of have to pause the testing and resume a bit. So yeah, it is, while the test sequence is on, we really stress to try and limit the use of exterior doors. It's not, people can still use them. It's not the end of the world, but if somebody's coming and going every minute, it makes it very slow and tedious for us to do it. Just some pictures of Michael Gilizan setting up our equipment, and so we're running tubes, setting up the blower door fans, and often up on rooftops, sealing up various vents, exhaust ventilators, and makeup air units are typical. So that's test day, and then prior to the test, there's just a lot of communication between the testing agent and the project team as far as getting drawings, planning where the equipment's going to get set up, and scheduling. So we want to try and target scheduling for, especially if it's for a final test, we want to do it right at the post-construction and pre-occupancy stage. Usually that works out. Occasionally there's a bit of a conflict where people are moving in, but the building really isn't super test ready yet. So it's something we like to avoid, and something that we stress project teams to plan ahead for. Certain areas, particularly like the garage, connections from the garage to conditioned space, really got to get those sealed up before we test. And then often on the rooftop, there might be some issues that haven't been fully sealed in yet. Door weather stripping or door sweeps are another thing we like to have finished. So we'll do a pre-test site visit a few days before the test, which is generally just like a 1 to 2 hour building walkthrough. We need to coordinate building access, making sure we've got access to all the rooms of the building for test day, and then just coordinating HVAC shutdown, which sometimes requires an external contractor. And then every once in a while, there's extra security concerns, or if let's say we're doing smoke leakage or detection of air leakage locations with smoke, we might need to do a fire alarm bypass. So some lessons from so far that we've accrued, just to get that test zone boundary clearly defined with project teams. Sometimes project teams aren't clear on where the test zone extends to and what openings should be sealed. And I'm thinking particularly below grade, that garage to say elevator vestibule interface doesn't always, sometimes it's a bit of an afterthought, or even on the roof, really getting clear on which zones are part of the test zone that we do expect to be sealed. Test timing kind of goes hand in hand with that, making sure that you're timing your test for when all those interfaces are sealed. If there are unfinished openings, how are those going to get temporarily sealed for the test? We've found some trends in test result versus building type that I'll go into real quick on next slide. And then just the importance of on-site support from the project team, just having a main point of contact to coordinate access, HVAC shutoff, observing for air leakage locations if that's part of the scope. And then testing costs. Generally, some large buildings can be in the 10 to 15,000 or more, but it really just depends on the test scope, right? If you're doing multiple tests, that's of course going to drive it up. If there's a lot of coordination for security or travel time, those are other factors too. Guarded testing, I'll let Randy speak to that. I just wanted to quickly go into, oh yeah, just a trend about results we're seeing with building types and shapes. It turns out low buildings, large footprints where you've got a slab as a higher percentage of the overall surface area, that's gonna provide a better NLR result, all things being equal, right? Buildings with large monolithic assemblies where there's fewer interfaces between different assemblies, those are all kind of favored for that normalized leakage area test result. Buildings with no operable windows too, of course, have an advantage. So examples are large service garages, arenas, warehouses. Just the building type and the shape can often counteract older, leakier structures, things like overhead doors. So that's sort of something that's surprised us, is how well some of those buildings do when we do see some leaky overhead doors, but all that, despite that, they still test okay. So yeah, it's good to compare like with like, I'd say, when you're trying to do some benchmarking, figuring out what similar building types are getting.
And Kyle, thinking about timing, maybe we would pass over to Randy at this point and we can come back to some of your other comments about finding air leakage locations and so on.
Sure.
What Kyle was mentioning that he put on the slide there, that guarded testing is a little different. And Randy, I'll just kind of set this up. The thought is, boy, I got a large building, it takes months and months, maybe years to build. Kind of like to know how I'm doing along the way, or it's such a large building, I can't possibly shut it all down and try to test the whole building at once. So there's this concept of, could we do guarded testing? And I'll ask you in the next 25, 30 minutes, just help us understand that and some of the challenges and opportunities associated with it.
All right, awesome. Can you guys see my screen?
Yes.
Okay, great. Yeah, so I'm going to get into guarded testing. Yeah, I work for Building Enclosure Labs, Inc. Started the company about 5 years ago. I think I pressed the skip button extra time. And yeah, we do quite a bit of like building science and education, focus on the building industry, education stuff. A lot of us, including building knowledge and people they work with, trying to get more into more active stuff, more in-person stuff. Still love webinars, but yeah, I think people are interested in having a little fun and a bit more networking nowadays. So some examples there, and you can see some blower doors in the background and some work we've done with Enbridge in the past and some training, mostly for other engineers and researchers has been our focus. And we also do some blower door testing. Most of the times that we pull out a blower doors for forensic work. A lot of commercial buildings, different issues with them with air leakage and trying to diagnose heating, cooling problems, condensation problems, comfort issues, that sort of thing. There was mention of, I did some work in Outer Mongolia, kind of a cool thing I did when I was in my 20s. Maybe when my kids are out of the house, I can get back into doing fun stuff like that. Yeah, so I did publish a data set of blower door numbers for houses in Outer Mongolia in the suburbs, essentially. And a funny little story, those two guys at the bottom right that I'm testing with, the guy on the far right got kind of excited. He said, "Oh, you're sucking all the air out of the house. Aren't we all going to like die of suffocation?" And so when you do blower door testing, anyway, that's pretty obvious, but we're only dealing in the 100 Pascal range, as we're like atmospheric pressure kind of goes up or down 5,000 Pascal. You're not going to notice it, but there are other safety issues with air tightness testing. Often you're going on job sites where it's really dusty and you turn out all these fans that can make a bit of a mess, and handling a lot of cables and trip hazards and heavy extension cords. I think it's very similar to other construction things, but that was a funny thing from this photo here. Yeah, often we're also pairing it similar to Building Knowledge's photos with infrared, you have pressure, no pressure, do things highlight, do things light up and then disappear that it's due to air leakage. With smoke, a lot of people love theatrical smoke. The client in the middle photo, he just loved it. He thought it was like the best thing ever, seeing us doing that to basically very clearly demonstrate that where that spray foam was interacting with that edge of that cantilever, it was not airtight. I got to throw recognition out to my co-op student, Amrit, who put together some illustrations for me that I'll be using for my example. So good job, Amrit. He's graduating next April. Anyway, people can look him up on LinkedIn. So testing large buildings, whole building air tightness testing, we're trying to capture the whole envelope. And that is the preferred method of testing. And so you'll hear that reinforced a few times as I'm talking. If you could test the whole building, test the whole building. And sort of the red outline there is meant to capture the whole envelope. But there's some limitations, and some of them, kind of alluded to previously. So phase completion, the lights are on and customers are coming in and out of the foyer and the commercial spaces down there, or the first couple stories of residential, and the top stories of the building are still under construction, don't have windows. And so finding an opportunity to test that building can be very difficult. Or when buildings are done in phases horizontally, where this chunk is done and then the chunk beside it is done and they're interconnected. It's hard to test the whole building at one point, or if not, impossible. Also, if the testing is linked to people's performance targets and getting paid, that test has to be done so that they can get substantial completion on a part of a building. The other thing, and Gord had a nice slide up there on stack pressure, warm air rises. So when it's cold outside, you're going to get differential pressures through the building. And so that would be another reason why commercial test standards, why I've always assumed they're a little higher than houses. Commercial buildings can be taller. And so 75 Pascal, might water down some of these stack effects. I love this photo. This actually from Denali Jones had this photo, which very clearly shows stack effect, the ballooning out at the top and the sucking in at the bottom. They're heating inside of that tarp, and it's kind of chilly outside, so that hot air is rising. And so we see the same thing when we're doing blower door testing. So to test a large building, often you need very good weather, not super windy, and the right temperatures. And then you need a period where the air barrier's installed, but the building's not occupied, and that's just not always possible. So what are your other options? So suite testing is fairly common. There's some mention of LEED. I sat on a technical committee for CHBC at the end of my time with LEED, and I was very disappointed that LEED version 4 never picked up whole building air tightness testing in the standard at all, even as an optional credit. But they do have suite testing for environmental control. Basically, if you're going to allow smoking in your multi-unit residential building, you don't want your neighbors to be able to smell it. The different suites should be relatively airtight. So not just the envelope, but to each other. And so that's a pretty easy test that can be done on a sampling basis. And that kind of happens all the time for a variety of reasons on different projects. Trying to use it to estimate the air tightness of a building, it's just pretty weak testing wise, because only a small portion of the air that you're sort of drawing through your blower door is actually coming from the envelope. And so you might be able to identify leaks and take photos of them and identify issues, but to use it to quantify how airtight a building is, it's a pretty rough way to do it. You don't get a whole lot of information. I think Mariana Tucci from U of T, they published a paper on this a couple of years ago where they tried to look at the limits of getting something useful from doing compartmentalization testing, even with guards. And I think it was pretty limited, in my opinion. You could go a little bit bigger and test a whole floor. Now you're just dealing with the floor slabs and less penetrations through separating walls between suites. And somewhat similar to suite testing, you will tend to be drawing most of the air from floor to floor. And so you get a lot of, or you sort of get a limited picture of the actual envelope leakage if you do that. There tend to be a lot of bypasses from floor to floor, plumbing, communications, those sorts of things that aren't always sealed up so great, or when you're doing the testing, they're not sealed. So that can be quite challenging. And then that leads to guarded testing. So say you're doing, in this example, a floor test. Well, why don't we basically limit the leakage, from these neighboring spaces by operating them at the same pressure as our test, and then hence negating flow between the guard areas and our test zone, so that we're basically measuring just the envelope leakage. And that's the ideal sort of scenario when you go to do this test. There's references to this in various standards. I think still today, these references are fairly limited. There's not a whole lot of actually big building guarded testing going on today. I see lots of proposals out there, but I haven't seen a whole lot. There hasn't been a whole lot published. And there are some references in various standards on the Toronto Green Standard. They basically allow it. They sort of have this language, if whole building is not feasible. I think it gives them a little bit of an out that if you did a guarded test for some ridiculous way of trying to game the system, they could call you out on it. And they present basically a sampling protocol for it. I think, Gord, you were part of that sampling protocol, I would guess. I think you were an early advisor to City of Toronto on this.
Yeah, I would say we were sort of peripheral to it, but yes, we took experiences from residential, single family, and said, what's practical. So in terms of the sampling amounts, so yes, we were.
Yeah. Awesome. And other various standards, you see sort of littered through them, that if you're going to test adjacent zones and try to maintain the same pressure, they do give some language about, well, what do you mean the same pressure? Is it exactly the same? And the numbers they have, plus or minus 10% in 2 of them, 3 Pascal in 1 of them. If you actually do this testing, those seem like ridiculously large variances. Like if you're testing at 75 Pascal, you should be able to control the 2 spaces like better than plus or minus 7. The resolution of the sensors is quite low, but even beyond that, it's pretty loose. Like if you're worse than that, you're kind of doing something majorly wrong, I think. So I think that those numbers are probably fairly aged before people had much experience on them. Would love to hear if I'm wrong about that and not part of that conversation back in the day. So some limitations of guarded tests, a slight pressure difference between the guard zone, the test zone can skew results. And so we're trying to maintain the guard zones at the same pressure. But in this case, if the guard zones are at a slightly lower pressure than the test zone, it can draw air from them and not run through the blower door. So that lends itself to some error. And so I'm going to go through some calculations illustrating this. I admit I have an engineering background. I've taught building science course, a bit nerdy, that kind of stuff. So I like calculations and putting numbers to things. And so there's a bunch of equations here, but essentially we're going to estimate how much airflow is coming, through the envelope, the stuff you're trying to measure, how much of it's coming from the guard areas, and then how much of it's going through your meter, basically what you use to report the results. And we'll run through just 2 different scenarios there. And so for my example, there's a certain wall area, there's a certain floor area. Once you're dealing with multi-unit residential buildings, it's very typical that your guard area is very large and your envelope area is much smaller. So that kind of lends itself to, if you have air leakage through your guard, it tends to be a big number. The other part is your envelope area. So we're using 1 here. So this is a pretty good building, better than average. Anyway, I just used the number. I thought 1 was a nice round number. Anyway. And the guard, it's difficult to even temporarily seal up these guards, but say you put in a little bit of effort and there's not a lot of published data on how well you can even seal these guards. Nobody really measures this kind of thing, but say you got it half as airtight basically as the envelope at 2. And, say that you're testing at 75 Pascal, it's kind of where the ratings come from. and say that your guard, you're really close. You're within, 0.1 Pascal. That sounds pretty awesome. You're way better than all those standards. So if you go through and calculate the flow rates under those conditions, and there's a little bit of funky stuff that goes on here, but your envelope for that area would be 180 liters per second. Your guard would be negative 39. And so what's happening is you're drawing air into the space. Some of it's going out through your blower door. And I admit this is kind of advanced topic stuff, but I was looking at the list of attendees, and some of those people are looking for advanced topics. Some of it's going through the blower door, and not an insignificant amount of it is not going through the blower door. It's going into your guards, into your guard zones. And so you're measuring a lower flow rate than what's actually going through your envelope. And so you would get normalized leakage rate of 0.78. And so that's 22% lower than actual. And so you're kind of cheating a little bit here. Now, in reality, when you go to do this test, we were talking about it before the call, you tend to test at a bunch of points up to the rated point and beyond it, and then you interpolate. And that's for some reason the standard way that we do it. So you're probably not -1 Pascal at every test. Probably your points are like bouncing up and down quite a bit as you're doing this. And the experience you'll hear from people doing guarded testing is sometimes when they do it, it's just not working out. The numbers are jumping all over the place. Even when they try to retest it at the same pressure, they get quite a different result. I'll walk through another example. So say your guard is 0.1 lesser pressure if you're at negative 75 Pascal. So it's negative 74.9 Pascal. Then you got air going the other direction. So your normalized leakage rate is 1.22 when it should be 1. So that's 22% high, but maybe that's okay. Like if you're aiming for 2, well, who really cares? You passed, you're good. Check. I can move on to the next project. Everything's good. The energy modeler is not going to have to work some kind of magic to try to figure out the implications of failing the test or whatever. Next, what if you could seal up your guard better? So basically the floor is separating the test zone from the guards. What if you put a lot of effort into trying to seal up those floors, like yourself when you're there? Lots of painter's tape. You got a whole bucket full of it out there, lots of laying plastic on things and temporarily taping things down and really going to town. I don't even know if this is frankly achievable on your average building, but you could minimize that error by better sealing between the guard and the test zone. And here we're getting down to 11%. Probably 11% error is probably pretty awesome, to be honest, with these tests, like plus or minus 10% is probably like unrealistically good for these tests, I would say.
Is it
just to give you guys a sense of it? Yeah, go ahead.
That
Gord.
idea of lower the numerator, right? It's the lower, and it's a nice way to say, okay, let's at least do some, rather than just using the fan to create the pressure. Let's try to do some taping and sealing. So thank you for that. You can increase your sense of accuracy, I guess.
Yeah. So if I get an excited call from someone who's in the middle of doing this testing that may have attended my training, or Gord gets this, the kind of things you're telling them is like, well, is there any way to like temporarily seal your guard better? Like if you guys are lost and in a panic and you think you're going to be there until 2 o'clock in the morning, things are just not working out. Get that tape out and start sealing as best that you possibly can. And
you could imagine in this building, for example, the elevator doors. Oh, okay, there's a big leak. Stairway doors. Oh, maybe I can.
You also have leaks to bypasses.
Right.
And so I didn't discover this by any means. This was noticed a long time ago as people started getting into this, really on the West Coast in Seattle, where my understanding the first projects were done with blower doors like this. David Straaten he's now at RDH in Toronto. He was out in, I think he was in Seattle or Vancouver. I used to work with these guys too. He produced this very nice graphic. It was published in the OBEC magazine, looking at some of these errors. And there's a lot going on here. It's a plot that only engineers could possibly love. But the major y-axis is an air, and then along the x-axis, they got the size of the cumulative hole between the guard zone and the test zone, and that's in square meters. And then I think that's the z-axis, is the actual leakage rate of the test zone. And so we were doing 1. That's probably a pretty good number. How to make my thing show up there. Me pointing at it doesn't really help people, I guess. And this is for a very specific project with a certain area and all this kind of stuff baked into the background of it. But, you know, we were around 22% and we went down to 11. But you can see what he's trying to illustrate here. What he's trying to illustrate is that once you have a very tight envelope and you have fairly large leaks to your guard zone, a very small difference. Oh, sorry. So yellow is 0.01 Pascal. Green is 0.1. So that's kind of where we were playing. But you can see 0.5 and 0.1. Your errors can balloon up, essentially. And, you know, that pressure difference, you might think, well, come on, you know, I've got lots of resolution on my little manometer I got from Gord. You know, I'm doing pretty good here. Often when you're doing these tests, those numbers are bouncing around a little bit with wind. The other thing is, you know, often we're doing these tests at just one point, like across your guard. And so if you have a bit of a sprawling area, you know, your guard could be seeing quite a range of different pressures across it, really. And so you can expect there's going to be some air there. And, you know, I think that this caused a lot of challenges when people are doing guarded testing. Another ex-colleague of mine. Oh, I had a timer on here, so I'll have to speed it up. Denali Jones, he's now with the Air Barrier Association of America, doing good work there. He actually published some results from a guarded test of like one of the first buildings those guys did in Seattle. And you can see basically the blue in the cross section there are the test zones, and then the pink are the guard zones. And the great thing here, he actually provided results for each. And so levels 12 to 13, 21 to 22, 31 to 32, all of those have the same envelope area. They're basically identical floors going up. And so if we presume that they have relatively basically the same air tightness, and say that all this guarding error is like a huge issue and totally ridiculous, you shouldn't bother measuring it, you're just kidding yourself. Well, actually for him, he found his averages for those zones like 0.218, 0.183, 0.19. Yeah, that's like a factor of 2 difference. Is that a real difference? There's probably some difference. Like he did find kind of a correlation between positive and negative. So what's the chance that both of them were low or both of them were high, you know, that sort of thing. But, you know, Seattle, he's really aiming for 0.4. So yeah, he's all good, you know. There's not a lot of publications out there like this that are kind of sharing with everybody, you know, the level of kind of precision we're really talking about. The other part, and I would encourage people to look up his paper, it's online somewhere. He does walk through like a bunch of measures they did to even get results that were this good. Like he is doing stuff that I'm not seeing on a lot of projects. And yeah, so definitely worth looking that guy up. We're trying to get a study going, him and I, looking at some of these errors and what we should really do in standards to sort of address them. And, you know, one of the only thing I've really done study wise is just think about what other errors could there be. So uneven guard pressures, I talked about, you know, across the floor, you could get some variances in pressures. You know, maybe you have a bunch of manometers. You're showing up with, you know, a truckload of blower doors anyway. The manometers are just left in the cases. I guess that sells Minneapolis a bit more than Retrotech, not giving preferences, because I think in Minneapolis software, you can like digitally average them quite readily. And that's something that Retrotech would have to adopt to. The zone bypasses. And so typically your blower doors, when you're testing these buildings, are in stairwells. A lot of these buildings don't have operable doors on the outside. It's a real pain in the butt to install a blower door and a sliding door, frankly. So often we're using the stairwells and we're trying to connect them to the outside. So often the stairwell you're connecting to is not actually at the same pressure as the outdoors, even though you've tried to leave a door open at either end. That's not always the case. Leakage from the zone to the bypass, Gord mentioned, to the elevator. Often that's a challenge to try to seal up in a decent way. You go around the whole thing with thick painter's tape and whatnot, but it's not perfect. Differences between the zone bypasses. So once you're getting into big buildings, you have multiple stairwells. And if you have to have multiple blower doors, the bypasses aren't even necessarily at the same pressure. This is really like a review looking for errors that are potential. Gord helped pick the number of floors in the Toronto Green Standard. And so, I don't think anybody did like some sort of error analysis to say like, hey, we need every 10th floor. Really, do we need every 5th floor, or is every 20 in a monster okay? Slowly as we're doing more of these and collecting more data, I hope we can inform that and start optimizing it a little bit. And then the last one, when you have a zone bypass on the outside, so it's hard to do without a visual, but say your stairwell is on the outside of the building and you do a test and you're doing guarded, what's the envelope area? What do you do with the stairwell? Do you include the outside envelope of the stairwell? Well, that's not even part of the test. Do you include the length of the stairwell on the indoors? Do you just take the lowest? I feel like if we get into guarded testing in a serious way, there's still lots of like standards type stuff that folks need to think about. So we're hoping to go and review all those things with a little bit of modeling. And if anybody can think of more errors, I saw some real smart people on the list here. Please send me an email and say, hey, Randy, you missed like, the 3 biggest errors or something. I'd love to get those emails. Don't hold back. So this is my last slide, some takeaways. Avoid guarded testing if possible. Like I have clients that call me up. It's like, oh, I thought about this thing. We could do this and do this, do this. It's like, yeah, dude, can we just test it all in one go? That makes everybody's lives so much easier. It's so much better. I'm sure Gord has this chat with and Kyle with these very ambitious engineers that are working for home builders to get these big ideas when they've heard of guarded testing. If you're doing guarded testing, like one direction the standards could go is they could just set up testing requirements once you're doing guarded to make sure that whatever you're doing is conservative. So you're doing guarded tests. If you follow these rules, you're only going to get a bigger number than reality, not a lower number. And so that, I would guess, is where the ASTMs are going to go, but we'll see. Minimize that error as best you can. Sealing between the guard zone and the test zone. The second one there, minimizing errors. If you can test multiple floors at a time and kind of capture more envelope in a single test, that minimizes that error essentially. That's a good thing. And then my last one, once again, avoid guarded testing. So this doesn't work out with Venoth's explanation that you only get the money for Enbridge if it's a guarded test or a whole building test. And what I'm kind of suggesting here is like, well, maybe just try to really seal the snot between your guarded zones and your test zones. And if you can, don't even bother doing the guards. Like, don't bother pressurizing them. Just try to minimize that as best you can. We've long been testing townhouses that way. When we test a townhouse, or a row house, we test a slice of it, one unit. We don't guard the two beside it. We just put up with that air leakage, and you tend to get crappier numbers for townhouses, which I'm sure Gord's probably been involved with testing 1 million of them. And that's all I've got.
Leave that slide up because I think there's good takeaways in it, and thank you for that. I think it's really important to reiterate what you said. Doing the testing is the most important. If you can't pressurize or depressurize the entire building, but you want to find your leaks, guarded testing still makes sense because it helps saturate the leaks. What we're hoping for, to your point, is kind of building a database. And this is, I think I could speak for Venoth, but he can certainly chime in. What Enbridge imagines is, what if we did some guarded testing and then did the whole building and had more information, if you will, as to whether that makes sense or not. And that's what Enbridge is trying to do, is trying to help the industry get a sense of what this is all about. So guarded testing is useful for, at the very least, for diagnostics and improvements. Now, we're still, the jury's still out as to whether how meaningful the results are, say, from a test standard perspective, but a comparison before and after one zone to another, I think makes a lot of sense. So Randy, that's really good takeaways. I love, as you said, if somebody here on the call has things that they have interest in testing, I know you'd be, this is what you do all the time is think of these kinds of research projects. So thank you for that.
Sure.
If you don't mind, stop sharing, and we're getting close to questioning here and a little bit of wrap up. Kyle, I think we'll put our slides back up.
Sure. Just a sec here.
Venoth, did you have a comment you want to make? I know we have some final slides for you, but any particular comment on what you heard Randy say?
Well, no, that's some great feedback on whole building versus guarded. And yeah, guarded may not be the most accurate approach, but sometimes it ends up being the only option for some of these builders and developers, just due to the construction cycle. So those are some good points on how to minimize error. So it's good to know.
And then I'll just speak to, if you're interested in this, and as Randy mentioned, there's some great names on the list. So perhaps you guys are all already will know about these, but he spoke of, and I spoke of testing that's being, a lot of more testing has been done on the West Coast. And because of that, they've done some really good guides. BC Housing has this excellent guide on achieving airtight buildings. The multi-residential air leakage control document from CMHC is pretty helpful. So there are some great resources out there. And then the testing firms themselves, and you're hearing from Enbridge as well. I think we'll go to the next slide, Kyle. We mentioned guarded, and you've now heard from Randy, but let's go back again and just highlight, Venoth, the incentive, and give us a little sense of the timeline. Where do you see this headed? Have they made advances on this? That is, a decision been made as the length of time the program will be open?
Yeah, great question, Gord. So we haven't been given the official go-ahead for 2026, but it is highly likely that this program is going to be available in 2026. That's kind of our inclination at this point. We should be actually hearing back very shortly in the next week or so from the Ontario Energy Board related to the filing and the improvement of this program being extended for one more year. So for sure, it's going to be extended. We're anticipating it to be extended for 2026. And after that, we still do not know how the program will probably look in the future. So knowing all that, I would encourage everyone to consider, if they have a project that might be on the fence for testing, to go forward with it and to use this incentive to kind of justify the financial implications. There's so many benefits that we can see. As I mentioned before, you're going to be able to get 80% of your testing costs up to $30,000 per project. And from my experience, there hasn't been too many projects that have hit the threshold or the upper threshold of $30,000. It kind of, that's been around the range. So this incentive has been able to make airtightness testing a lower cost endeavor for your projects. Do you want to go to, is there next slide? And then I just want, I just want to talk about the eligibility. Once again, it's a little bit confusing, but this is a Part 3 building program. So anything in the Part 3 space, so any commercial, multi-unit high-rise would be applicable. There needs, the minimum size of the building tested needs to be 25,000 square feet or larger, located in Enbridge service territory. And another thing I wanted to mention is this program is applicable for new construction as well as renovations or deep energy retrofits or change of use projects that may exist out there. So it isn't only for new construction. If you're doing a large renovation of a building, deep energy retrofit such, that could be also applicable. So reach out for about that.
In fact, there was a question from Roy. Thanks, Roy, for listening in. Are we seeing airtightness testing for existing buildings? And Randy's pointed out that there are municipalities that are looking at decarbonization strategies for their facilities, and that's been done. And Kyle, you've been doing a fair bit of that. I think I mentioned all the ice rinks in Cambridge area, for example. You're working on some others. Tell them about the one we're excited about, wondering if it'll go ahead. That Randy, you and I and Kyle were talking about, there's an RFP out for testing. Go ahead, Randy.
Yeah, sorry, I don't know. I wasn't sure if it was Kyle or myself. Yeah, I think you're talking about Toronto Union Station.
Yes.
They had an RFP out, I think, for an energy audit. Kind of one of my colleagues looked after our end of that. And one of the things in the specification, as you guys were mentioning, people come up with these specs and they put them out there and copy from a previous project. And sometimes I think you can get a bit lost in translation going from one building to another. So yeah, Toronto Union Station was a recent one out, and I think they put through an addendum to people's questions, because probably a lot of smart folks like yourself came back and said, oh my gosh, trying to test the entirety of Toronto Union Station, including the mall and everything. And Lord knows how many tunnels go into there for service chases and things like that. That's probably quite ambitious. And also there's very few hours that the facility would be available to even do testing without people, large crowds of people coming in and out trying to reach the subway. And so not sure if it's even physically possible to do it. And then secondly, I think you would lend yourself to, well, really you're trying to find, major leakage points, and, quantifying the whole building. Is there a whole lot of value to that in a case like this, which is a real odd one? Right. So anyway, I'll let you expand on it.
Yeah, I was just going to say, we kind of envision mobilizing the entire building science community. Anybody with blower door, please arrive. We'll just do a sort of a crowdsource of blower doors on a given Saturday evening. So thank you for that. So yes, there is interest on that. The other question came up, and Randy took a bit of a stab at it, but Kyle, I think you're going to want to mention as well. Did Mattamy specifically take any extra measures in order to achieve that 1.2 number? As you recall, the Toronto Green Center number is 2. So you imagine 1.2 is a pretty good number, not as good as the London number, 0.54. But Kyle and Randy, you had some experience with that at the design side. Kyle, talk a little bit about the training that that particular builder committed to as part of their work.
Yeah, so with Mattamy, we started off doing a few tests for benchmarking purposes, and then that's since morphed into doing some more upfront training with their design and construction team, which I think has been really helpful, just to get everybody on the same page, identifying, okay, what is our test zone boundary? What are all the materials and assemblies and components that make up for it? Coming up with some protocols for doing some mock-up testing, some suite testing. So I think part of it is just spreading awareness among the project team. Like, I know there's been some good studies about how once project teams understand that, oh, we're going to be tested, then all of a sudden it's sort of a contagion effect where they tend to pay a little bit more attention across the board on some of the details that help.
Exactly. Even highlighting, we know architects in many cases. Well, I'll give you this experience. When the Army Corps of Engineers was first starting their airtightness efforts, I happened to be at a training session put on by a company that offered air bearing materials, and I was sitting beside the chief engineer for the Army Corps. I said, "How's that going?" He says, "It's interesting. It starts at design. If the architect draws the red dotted line on the cross section of the building that is indicated the air barrier, what is the air barrier, we do really well. We always pass. If the architect does not identify the air barrier and the components of, we seldom pass." So even highlighting to a construction crew, this is your air barrier. Anytime somebody puts a hole through this, anytime you make a penetration, seal that. So I like your idea there of just the awareness at the site level is pretty interesting. There's a couple other questions that I'll handle, or at least talk about. There was a question about, do you have to seal the egg crate for open return systems? And typically that's within, and Randy's answer, but I'll just highlight it, that's within the building enclosure. What you want to do is find where's the fresh air intake at source. So is it in the rooftop unit? Is it some a ducted fan? So typically you're going back to the enclosure. Now, if you're trying to do guarded testing and using a drop ceiling, we would say don't use a drop ceiling as the guarded tested plane. But typically, an open return to a sealing space there's really no value in sealing that off for a test. So thanks, Randy, for answering that. Ty has asked, do we have experience with guarded testing on large buildings? And I think hopefully Randy's now answered that to say, yes, indeed, there has been experience, and the experience is still lots of work to be done, and exactly what the results mean and your confidence in the numbers. We'll say again, you can have confidence in doing the test because it helps you identify leakage spots, and it gives you a sense, and you would try to be as conservative as possible in your test protocol so you can be confident in it. But you heard from all three of us, best is to do whole building where possible. The idea of guarded testing, I think, Kyle, you would agree, takes a lot more planning and pre-prep. And then your results aren't you're not nearly as confident in your results. So what you may see as a simpler step of guarded ends up being not as easy as you thought. Let's see if there's any other questions. I don't see any others that are open. Did we miss any? Any other questions from the crowd? Or and then maybe I'll ask as well. So Randy, do you have a sense now in Canada? I remember at one time the figure was less than 500, this I'm going to say 7 or 8 years ago, less than 500 large buildings in all of North America had been tested. What's your sense now in Canada from your experience? What would you guess what is the total database of large building testing that's been done?
Yeah, I wish I could lend more to that. In my the end of my time at RDH, we were commissioned by Canadian government to do a study of air tightness testing of large buildings. But basically, you know, if it was adopted into building code, are there even people who are capable of doing it? I think seemed to be the big issue or the big point of interest. But part of that is Lauren Ricketts, who you showed a previous slide from. He did a study of all the data that he could find, including RDH's database. And I think that's where that 500 number comes from. And yeah, you know, I think that was at least 5 years ago. And so there would be a lot more. How many people are sharing? You know, when you test those ice rinks, that data's, you know, not often public. People would have to know you and email you for it. And so it's probably timely for someone to go and check in on that again and put out those kind of data sets, because there is quite a bit of testing going on. You see lots of RFPs on all kinds of buildings from the federal government and lots of decarbonization planning type work being done in all kinds of facilities for different municipalities in the Ontario government. As I'm sure that's spread across Canada. So there should be a plethora of data sitting out there. It's just not collected.
And my opinion would be it's certainly more than tens, it's hundreds, it's not thousands of buildings yet, it's hundreds that have been tested. And that's really the call to action, I'm going to say, as we close up here. The call to action by Enbridge is saying, and I'll go right back to the original premise of this, could we help the industry? Could we do market transformation? Could we encourage some testing to get started, to get the infrastructure in place? I mentioned in Toronto now there's 3 or 4 firms that do what we do, and we're pleased to talk to anybody about that. But let's at least have the equipment available. Let's work away at some of the standards so that we have protocols that people can be trusted on. And folks on this call can now be confident that of the firms that are testing, there is a pretty good understanding of the protocols, the test standards, even the benchmarks as what needs to be done. You heard from Kyle about variations in the different types of buildings, and you heard a pretty nice conversation about one of the sort of holy grails has been the guarded testing, and we'd say be guarded about guarded testing, I guess is the way to put it. I could use that.
Well done.
But I think so what I would suggest, and maybe Kyle, go back to Venoth's contact information. If you have a project that you're thinking of that I would say get in contact. There's $ availability of this program, and start your first contact, I would say, would be with Venoth, and he'll be able to help you understand how to make the application. It's been pretty simple from an application process. So I'll say, Kyle, any final thoughts?
Yeah, I'll just echo our our ability and willingness to test all sorts of large buildings, various types. We've done a lot of it, so you know, at this point, it's no big deal. We keep it pretty simple. Try and have at least amount of disruption for project teams. I know there's plenty of other things they've got to worry about and think about, so we try and make it relatively smooth, hassle-free process. We've been through a lot of it, so.
And so knowing that this is going to be part of your world someday, testing buildings, when would be the first time way to try it? And to my mind, the answer is now. Get started, do one, see where you're at, I think is what we're deciding. Venoth, do you want to make some closing comments? And we're right at time, so perfect timing.
Sure. I just wanted to thank everyone for their time today on this busy afternoon. We got to hear some great speaking from the folks at Building Knowledge and Randy at Belly. So appreciate everyone for their input and taking time to be part of this air tightness testing webinar. As Gord mentioned, time is running out, so reach out if you do have a project that you are considering testing, and we'll see if we'll be able to, apply you to the incentive.
And a special thanks to Randy. I just really appreciate your experience. You had said nerdiness, but I'll say your experience on this. It's fantastic to have you on here. This webinar was part of a series that we put on in conjunction with Enbridge on a regular basis. Please sign up for our newsletter and follow us so that if there's other topics, many of the topics are residentially based, but we'd be pleased to have you on any calls. And I'll say again, thank you, Kyle. Thank you, Randy. And thanks everybody for being on the call. Hopefully you found it useful. Take care, Emma and Kimberly. Thanks for your help. Talk to you later, gang.
All right. Bye-bye, everyone.